the European Centre for Particle Research. CERN is revealing information on a brand new particle accelerator now. It is twice, 3 times bigger and as deep, discovering 3 new particles that could help us comprehend the origin of the universe and how it will emerge in the future. As of late, CERN researchers published results that alter how we see the universe. Below the surface of its head, there is a universe of innovative experiments, of strange particles and forces that they might appear in a science fiction film, unique from possible entry points to other sizes of particles that provide a danger to the fundamental underpinnings of what enigmatic mysteries exist in reality. Within these trials, let's find out, explore CERN's environment and discover the facts that can reshape our world, the entryway to the new dimensions. Wormholes might theoretically emerge unexpectedly in the sky, and the one explanation may be the revolutionary experiments carried out at the Large. What is the Hadron Collider LHC at CERN? Is the LHC, or Large Hadron Collider, the biggest and strongest in the world particle accelerator close to Geneva, crossing the French boundary? There are mysteries about Switzerland, the world's peculiar organization. Not yet be aware of secrets that could alter our perception of physics. Together with the cosmos, CERN, the European Nuclear Research Organization, runs this enormous scientific instrument, which spans more over 27 kilometers and sits far below the surface of the main purpose of the Large Hadron. Physicists will be able to use the collider to evaluate the claims provided by different particle physics hypotheses, such as the typical model that aids us understand the basic components that the LHC is the central component of the cosmos, operates by speeding up protons to almost the speed of light before colliding with them. When these encounters occur simultaneously, a shower of fresh particles that scientists research to learn more about nature's basic laws. It was by use of such experiments that often use the Higgs boson, known as the God particle. This discovery was made in 2012, helped us comprehend how particles acquire mass, which was a crucial in particle physics. The LC conducts experiments that are essential for comprehending things that occur under harsh circumstances, akin to in the immediate aftermath of the Big Bang. The information gathered may help us understand the origin of the cosmos and how, regarding the essential elements of matter, the LHC could reveal new. The Large Hadron Collider's dimensions are a crucial figure in perhaps revealing new dimensions of reality, dimensions that could provide insight into mysteries encompassing dark matter and the basic forces of nature. There have been worries expressed over CERN's high-energy tests, using rumors that they might produce black holes or strange matter that could present threats to Earth, but CERN guarantees ensure every safety precaution is taken, and the scientific community keeps a careful eye on various tests, investigations, and theoretical frameworks. Verify that any risky situations are quite rare. By its continuous investigation and findings that CERN keeps improving our understanding of the cosmos and illustrates the amazing powers of human resourcefulness and cooperation in the largest quest for knowledge. CERN's Hadron Collider LHC is not just an amazing technological marvel. It is a marvel of contemporary technology and engineering located under the Swiss. The LHC is 27 kilometers over the French border tunnel and descends to a maximum depth of 175 meters, making it the biggest subterranean world's particle collider and one of the most important tools in particle physics. Composition and operation of the LHC. The structure of a Large Hadron Collider is created to manage tests of extraordinary size of the main ring tunnel. It has a diameter and contains the collider of 3.8 m and includes two nearby pipes with parallel beams that each guide protons moving in opposing directions, bringing them up to almost the speed of a sequence of superconducting lights. These are controlled by magnets. These magnets are necessary for protons, preserving the course of the proton's path, twisting as they move at high speeds in order to maintain this. When magnets are working correctly, they are cooled to below space temperatures. Using cutting-edge cryogenic techniques, the Large Hadron Collider's scale is further emphasized by its dozens of magnets, such as using 1,232 dipole magnets. The 392 quadrupole magnets are employed in proton beams to concentrate the biggest rays and strongest magnets that conduct electricity, weigh 35 and have a length of 15 m. Tons for each of the LHC's comprehension of the universes. Constructing bricks, the main objective of the LHC will look at the basic nature of the cosmos by looking at the smallest elements of substance by speeding particles to almost the speed of light and running into each other. Physicists may examine the outcome. Collisions between subatomic particles permit researchers to test and broaden our comprehension of the conventional model of particle physics, which explains the basic particle behavior. Examine how the Higgs boson works. Particles gain mass and investigate darkness. Antimatter, matter, and the basic natural forces confirm the existence of theoretical predictions for new particles. Physics looks for proof of additional supersymmetry and dimensions are two of the one of LHC's greatest accomplishments was the Higgs boson was discovered in 2012. It supported important hypotheses on how particles acquire mass above the heights. Boson, the LHC has furthermore verified the presence of unusual particles. Such particles called tetraquarks are composed of 4 particles of quarks and pentac quarks composed of. These findings broaden our understanding of 5 quarks. Comprehension of hadronic matter, which creates an atom's nucleus beyond 3 dimensions. The look for additional. The Large Hadron Collider's dimensions are not just about comprehending the building blocks of the cosmos, it also encourages global cooperation. Hundreds of researchers from more than 100 nations collaborate at CERN to make. It is a real testament to international scientific collaboration via addressing some of the greatest. The LHC raises important physics problems. It is more than simply an experiment. Emblem of humanity's unwavering quest. Much information. How does the Big Hadron? The core of CERN's work is collider work. The Large Hadron is a research facility. Collider acts as a magnifying glass into the quantum world that enables scientists to examine the essential components of acceleration of particles in the cosmos. And collision, the LHC operates via beams of protons or heavy particles that accelerate ions to speeds that are comparable to. These beams of light move across a vacuum. Tubes that are sealed and encircled by. These are superconducting electromagnets. Cooling temperatures are applied to magnets, cooler to maintain than outer space. Their ability to carry electricity, the beams are pointed in the direction of the places where they collide. Combined with tremendous vitality, these accidents that momentarily recreate circumstances comparable to those that were right after the Great Bang, generating several different subatomic particles. Identifying crashes, aftermaths to examine these encounters, the LHC is including 4 enormous detectors. 1. The general-purpose Atlas detector is used for finding 2 CMS particles, like Atlas but with a distinct. Alice's area of expertise is Magnet System 3, researching collisions with heavy ions. 4. LHCb emphasizes comprehension. Distinctions between matter and These detectors pick up antimatter, details about particle mass charge, and momentum, assisting physicists in their testing, theoretical physics predictions, and look for fresh particles and forces. Among the most significant findings, the Higgs boson was created at the LHC, occasionally called the God. The Higgs boson particle verifies the Higgs field's existence, which is charge of celebrating mass for simple particles outside of the heights. Boson, which the LHC has shown strange particles that were before unknown, such when pentaquarks and tetraquarks grow. Our comprehension of the potent nuclear force that holds together atomic nuclei, scientific or theoretical risks. The Large Hadron Collider in fiction. As skills increase, so do theories and worries about the possible dangers of it too. Of the most talked about theoretical, one of the risks is microblack holes, with some speculating that they are high collisions of energy might produce tiny black holes that might present a danger, but scientific models show that any black holes generated would vanish immediately because of Hawking radiation. 2. The creation of odd, strangelets of matter take on a speculative shape of substance may potentially transform typical substance into a new condition. However, recent studies indicate that CERN, this situation is very improbable, has researched these issues in great detail, and has determined there isn't. All experiments pose a real danger to the planet, are observed by an international community of researchers and theoretical frameworks, verify that any risks are only conjectural. Concluding remarks. CERN and the Large Hadron, the future of physics. A collider is among the most. It is not an ambitious scientific endeavor. As a particle physics instrument, it is a entrance to fresh information that aids us solve the most profound mysteries of the world by carrying on with its cutting edge. CERN's experiment tests the limits of what we understand of the beginnings of the universe, the underlying forces of nature, dark matter's existence, and more dimensions as we continue our journey into the future. The LHC is a evidence of the inventiveness of people, global cooperation, and the CERN's quest for knowledge might lead to. Only time can reveal the universe's mysteries. We'll describe matter in a conceptual way that has more stability than regular stuff. According to the theory strange, anything might change with which it encounters the dread of. Connected to this hypothesis is that, in case collisions caused oddlets between the Large Hadron's particles, collider LHC, they may be able to start a disastrous chain reaction, turning all of the Earth's substance into strange matter, no matter how vast. Studies and safety evaluations conducted, released by CERN and the International Scientific. These issues have been handled by the community. Research has shown that if odd allows could in fact exist and were created at the LHC, they would very likely be quite unstable and degrades too rapidly to result in any changes to the composition of the Earth. Moreover, cosmic rays that are high energy particles from space on a daily basis hit the planet with a lot of energy, greater than the ones generated by the LHC. Given that these cosmic rays haven't produced strange matter's creation, a natural experiment indicates that strangelets aren't a real danger. According to the black hole theory, micro-black holes might be produced by the LHC, originates from extra-dimensional ideas. In the field of physics, several theoretical theories state collisions with high energy within the LHC could produce tiny black holes that would vanish quite immediately because a phenomenon called Hawking radiation, named after Stephen Hawking, a scientist. According to researchers, if small black holes were produced in the LHC, these black holes wouldn't be a danger, be so little that it would evaporate prior to their ability to communicate with the environment. In addition to the The energy at play in collisions at the LHC are, by human standards, they are enormous, remains far less than the cosmic ray collisions that take place naturally because there is no dangerous microblack hole observations have been made from cosmic rays interactions. It is very improbable that any that the LHC CERN would yield, in addition to independent committees, carries out thorough safety evaluations to guarantee that LHC experiments pose no danger to humanity or the planet. These reviews include theoretical, examines safety regulations and experimental information to address any possible risks while the LHC keeps pushing the limits of the experiments in physics are conducted with a great deal of accountability and scientific supervision, which guarantees that humanity gains from innovative findings without taking unnecessary risks. Theoretical hazards often seem greater, more believable than science fiction. Scientific results, the scientific agreement based on thorough, natural cosmic events and research are the safety of the LHC and its potential. There are little hazards involved with looking for monopolies that are magnetic are among the most intriguing and unusual experiments. The hunt for magnetic resonance at CERN. Imaginary particles known as monopoles that possess a single magnetic pole, such as in comparison, the North Pole or a South Pole. Common magnets usually include both existence of a North and a South Pole. Paul was the first to foresee magnetic monopoles. In 1931, he proved that their existence could explain why electric, since charge is quantized, it always occurs in distinct quantities as opposed to constant values in spite of their magnetic theoretical relevance. We have never seen monopoles. LHC researchers are still looking in search of proof of these elusive particles. If monopoles were found, they would transform our understanding of magnetic fields and may result in technological developments like new ways to transmit and store energy. Furthermore, the identification of magnetic monopolies would provide exploratory proof for the guts of grand unified theories and string theory, both of which seek to clarify all of nature's basic powers inside just one framework throughout the search. Because magnetic monopoles may appear esoteric, it is a prime example of the adventurous passion and inquisitiveness that motivate scientific investigation at CERN. The potential for exceeding the speed of light particles. Another unusual experiment at the LHC entails looking into the possible presence of particles that might move more quickly than the speed of light based on Einstein's hypothesis of the speed of light in relativity is the maximum velocity in the cosmos. Nevertheless, some theoretical frameworks indicate that the existence of hypothetical particles and always travel more quickly than light. If found, a tachon would essentially question how we perceive causation and spacetime, although the majority of physicists continue to doubt the existence of tachon's quest for such particles at the LHC shows that it is willing to explore even the theoretical parts of physics. The LHC's ability to recreate the early universe, furthermore, enables scientists to replicate circumstances akin to those of the early moments after the Big Bang. The universe collisions with high energy at the LHC create the quark, a state of matter, gluon plasma, which was only found in a small milliseconds after the initial bang via research. The goal of these plasma physicists is to comprehend the evolution of the cosmos from its original state of great energy into the organized universes that we see now, such as CERN experiments from the quest for magnetic monopoles for quark production. Gluon plasma highlight the range and aspirations of its scientific studies. The Large Hadron Collider's significance. The final result of the Large Hadron Collider. The goal is to advance the boundaries of human knowledge via particle collisions at previously unheard-of energies, which enables scientists to investigate the basic matter's characteristics and the forces that control the cosmos. The pursuit of the unknown reflects the natural curiosity and yearning of humanity to investigate the findings at the LHC has broad ramifications for our comprehension of the cosmos, origins, development, and final destiny. Moreover, technological developments, findings from LHC studies have useful uses that go beyond particles. Physics advances in sophisticated detectors, computers, and information analytical methods have helped to advancements in domains like material, information, science, and medicine. Technology, the LHC experiments further encourage global cooperation, motivating a fresh round of scientists. Researchers from all around the globe are employed, jointly exchanging information and skills to discover the universe's mysteries. This international collaboration emphasizes the science's ability to transcend borders and bring people together in the interest of the Large Hadron's knowledge. Conclusion. Collider is essential to contemporary physics is improving our comprehension of the basic particles and forces that the beginnings of matter are revolutionary. Experiments provide priceless insights, discovering the secrets of life by way of innovations in technology and worldwide partnerships. The LHC is a prime example of the spirit of scientific inquiry and the boundless possibilities of human inquiry. While we keep investigating the cosmos, using the LHC we get closer to responding to some of the most important inquiries about our existence and the location of the Large Hadron in space. Collider LHC has already produced revolutionary findings like the verifying the high boson in 2012, but the search for more CERN is planning as understanding continues. Several improvements and upcoming initiatives to push particle physics to its limits. High luminosity huge hadron even more. Collider. The high luminosity LHC, or HLHC. HHC is the next significant enhancement to the current collider is expected to become functioning in the latter part of the 2020s. The main objective is to greatly raise the luminosity by the quantity of collisions per second, which permits researchers to gather further information and examine uncommon occurrences in further depth. Among the main improvements are stronger magnets to direct and concentrate particles, beams with increased accuracy, new using technologies to improve, advanced energy efficiency detector, tools to get more accurate measurements of interactions between particles. These enhancements will allow the HLC to aid in the research of the Higgs boson by physicists. With hitherto unheard-of precision, look for additional particles and improve our knowledge of the underlying forces that control the universe's future. Circular. Beyond the HHC CERN, the Collider FCC is looking at possibilities for a bigger accelerate the circular collider of the future. The FCC's next generation of colliders would be around 100 kilometers in diameter. The FCC is 4 times the size of the LHC. Intends to destroy positrons and electrons, combine to create a really pure source of high-energy bosons for research. Circumstances in which physicists may identify if there are dark matter particles. Investigate physics outside of the norm. Model using SUSY's supersymmetry and additional dimensions, if permitted. The FCC's construction might start in the 2040s. Will be the next phase of our endeavor to uncover the mysteries of the quest for dark matter in the cosmos, and one of the greatest mysteries is dark energy. The nature of darkness in contemporary physics. Dark energy and matter, whereas normal, just 5% of the cosmos is composed of matter. Dark matter makes up about 27% of the total, and It is thought that the remaining 68% is dark. Energy is the power that propels the rapid dark matter growth in the cosmos. Dark matter's unseen mass cannot be directly seen to exist, is deduced from its gravity, impacts on the cosmos and galaxies, structures that experts believe to be dark. Weakly interacting molecules make up matter. Enormous particles known as axions or WIMPs that the LHC is currently investigating how. The role of the LHC in dark matter. Investigation to find the energy that is lacking in collisions of protons. If dark matter particles are produced, they may escape detection but leave an energy trail. Unbalanced and looking for fresh exotic particles that have the potential to become dark. Investigating matter in the Higgs boson to ascertain if it interacts with darkness. Dark energy is the power behind matter particles. In contrast to darkness, behind cosmic expansion, dark energy of matter is still even greater. Elusive, according to some ideas, it may be associated with quantum fields or alterations to Einstein's hypothesis of gravity, but the LHC is unable to directly find dark energy. Experiments that measure the correct Higgs boson might provide indications of how it fits into the bigger future structure of the cosmos. The FCC and other particle accelerators potentially assist us in comprehending these enigmatic cosmic elements, giving us nearer to resolving one of the most important physics puzzles.